Now we're thinking about magnetic phenomena, and in many ways they are very, very similar to electrical phenomena. In both cases, you've got some kind of a source that produces a field. In electrical phenomena, it was electric charges that produce a field, fill the space all around those charges with field. In the case of magnetism, the source is moving charge. One charge that might be moving, or a whole lot of charges, in other words, current. Most examples that we'll think about here will involve some current and the field, magnetic field that current produces. And just like in electrical phenomena, something else that's like the source wanders into the neighborhood that has that field and as a result feels a force. In the electrical phenomena, the source of the electric field is charge, and then another charged object moves into that region and feels the field, and therefore there's a force. In magnetism, it's a moving charge or current that creates the field, and then another moving charge or current comes into that neighborhood and feels the magnetic field created by the original current or moving charge. And then when it feels the field, there's then a force similar to electric field and electric force. Where it gets a little complicated is the kind of field that is produced by a source of magnetism. So let's imagine this. Imagine a long straight wire, and there's current passing through that long straight wire. Imagine that the wire is perpendicular to the plane of the blackboard, just coming out like this. And imagine the current is pointing at you, pointing straight at you. And we have a standard symbol to indicate the direction of something that's perpendicular to the blackboard or your paper and pointing out, away from the blackboard, away from the paper, pointing straight at you. And it's this thing here, a dot inside a circle. You can think of it as an arrow perpendicular to the plane of the blackboard, and then the arrow is aimed directly at you, and all you can see is the tip of the arrow. Think of the spot as the tip of the arrow. So there's current going this way, and current produces magnetic field. What does that magnetic field look like? Specifically, what do the magnetic field lines look like? And the answer is, in one sense, simple, in another sense, complicated. The simple answer is circles. The magnetic field lines are concentric circles, all centered around the source, like this. I tried to draw them more or less concentric. And just the same as in electric field, the farther away you get from the source, the weaker the field. So I draw field lines farther and farther apart from each other as we get farther away from the source. Field lines farther apart means weaker field. That's true whether you're talking about electric field lines or magnetic field lines. The other thing is, field lines have a direction to them. How do you figure out the direction for magnetic field lines? And for that, we have this thing called the right-hand rule, described in chapter 24. It's pretty simple as long as you remember that it has to be your right hand. Point your thumb in the direction of the current. Current's coming this way, so point my thumb this way. And then curl your fingers in kind of a semicircular way. And the way your fingers curl, that's the direction of flow for the field lines. So for the field, or for the current coming out like this, thumb in this direction, curl fingers of the right hand, and they curl around in a counterclockwise sense. So that's direction of the magnetic field lines. Like that. And it's similar if we think about current going the other way, still perpendicular to the blackboard, but now pointing away from you, pointing into the blackboard. And our standard symbol for something in that direction is just an X. Again, imagine that there's an arrow pointing in the direction of the current, and all you see is the very back of the arrow, the feathers that you might have at the back of an arrow. But again, just like in this case, the field lines are concentric circles around the current which causes that field. And the direction of flow for the field lines is indicated by the right-hand rule. Point your thumb in direction of the current. In this case, the thumb will have to be pointing into the blackboard, because into the blackboard is the direction of the current. So point your thumb that way, curl your fingers, and the sense of the curl tells you which way the field lines are flowing. My fingers are now curling clockwise. So clockwise is the direction of flow for these magnetic field lines. That's what field lines look like. What exactly is the direction of the field at any one particular point? Well, just imagine any point, say, and then imagine the circle centered on the current that includes that point. So we'll just say choose a point that is part of a circle we've already drawn, just to keep it simple. At that point, the rule for the direction of a field at a point is the same, whether we're talking about magnetic fields or electric fields. The field always points along the straight line that's tangent to the field line. So this circular field line means the tangent line right over here on the far right edge of the circle will be vertical. So the field would have to be pointing vertically, either straight up or straight down. And because the field lines flow this way, right, they're flowing up here to the right of the current, then the field at this point must be pointing up. And similarly, on another field line closer in, but in the same plane as the current, just like this was in the same plane as the current. Here you are at the far right edge of the circle, and so a straight line that's tangent to the circle at this point again must be vertical. So just like here, the field at this point again points straight up. But I'll draw it with a bigger arrow because this point is closer to the source, so the field has to be stronger. And then get really close to the source, but in the same plane as these 2 points, and the same plane as the current. Then again, you're at the far right edge of a circle. So the straight line that's tangent to the circle will be vertical. And again, the field here will be vertical and pointing straight up, because that's how the field lines flow. And an even stronger field, because now we're even closer to the source than we were here or here. And the same thing applies anywhere else. Let's say this point right here. At this point, the field will be pointing along a straight line that's tangent to the curve, so a straight line like that goes diagonal like this. And since the flow of field lines goes down and to the right, at this point, the magnetic field points down and to the right there. And then things would work just the opposite way. In this case, where the current is now moving in the opposite direction into the blackboard instead of out of the blackboard. So this point right here, in the same plane as in the same vertical plane as the current. So this would be the very top of the circle. And at the very top of the circle, a straight line that's tangent to the circle has to be horizontal. So at a point like this, the field would be pointing either straight to the left or straight to the right. And because the field lines are flowing clockwise, up here, they're flowing this way. So at this point, the field must point to the right. And then similarly, at the top of this circle, again, you're at a point that's in the same vertical plane as the current. This is a point directly above the current. So this is the top of the circle, and a straight line that's tangent to the top of the circle is again horizontal. So the field will point horizontally, and since the field lines are flowing clockwise, that means on the top here, left to right. And a bigger arrow to indicate a stronger field because this point is closer to the source than this point. And then just one more. Imagine a point on this circle directly below the source, still in the same vertical plane as the source. So this point is the bottom of the circle that is centered on the source, centered on the current. So at the bottom of the circle, again, the straight line that's tangent to the circle has to be horizontal. So the magnetic field will be pointing either straight to the right or straight to the left at this point. And because the flow of field lines is clockwise, down here that means right to left. So the field has to point straight to the left. And this point is the same distance from the source as this point. So the strength of this field will be the same as the strength of this field. I draw them with arrows of equal length. Now let's think about a slightly different way of picturing a current and its field. Imagine these vertical planes in which the current sits. We can see that in these vertical planes, the field is pointing perpendicular to those vertical planes. So now, imagine that we twist everything 90 degrees. So this vertical plane is now twisted this way. And so field that was moving in this way, in other words, moving from the right edge to the left edge of this paper. Now I'm just twisting my point of view 90 degrees, so the current is still moving from the right edge to the left edge of the paper. And this vertical plane in which the current sits, we're now viewing not the edge of that vertical plane, but the whole plane. It's as if we're standing right over here and looking at this plane. So the current was going this way through this plane. As I view it from this side, the current is moving right to left. So let's see what it looks like if I can see that whole plane. So when I see that whole plane, like I said, I see the current moving right to left. But whatever my point of view is when I look at the current, it's still true that the field lines are concentric circles that would wind around like this, with half of the circle here in front of the blackboard and the other half of the circle behind the blackboard. Here's the current, and so the field lines would be making circles like this. And as I pointed out just a minute ago, in the vertical plane that the current carrying wire is in, which is now the way I've drawn it here, the plane of the blackboard, the field lines are perpendicular to that plane. In other words, the field lines will be pointing either straight in or straight out. And which way they point is again determined by the right-hand rule. Thumb in direction of the current, and then my fingers curl this way, so that when my fingers are above the current, which is represented by my thumb, my fingers are curling in a counterclockwise sense as I see it from over here, but they're also curling into the blackboard. So at this point here, right in the plane of the blackboard, right in the vertical plane where the current sits, the field lines are perpendicular to that plane and pointing in, because that's the way my fingers are moving. So that's how you indicate the direction of the field in that case. All the field lines at that point, or all field vectors at that point, are pointing straight in. And then go back to the right-hand rule. At points below the current, which is represented by my thumb, my fingers are curling out of the blackboard. So below the current, the field lines would have to be pointing out perpendicular to the blackboard. And there's the symbol for out perpendicular. Just as this was the symbol for in perpendicular. So the field lines are flowing like this, counterclockwise from my point of view. So the field lines will be flowing this way. On the bottom, they come at you, and then they move up, and then they're moving away from you. That's how the field lines flow on this side of the blackboard. And then imagine the other half of the field lines, the other half of those circles behind the blackboard. Those above, those field lines would be pointing into the blackboard and then curl around and be pointing out of the blackboard below the current. It takes a little bit of getting used to think about this, but this is really the main point of thinking about magnetism. You have to think visually, and you have to move your hand around in order to find the correct directions, and don't be timid in moving around, because that'll give you the wrong answer. uh, don't be afraid to twist and turn. Uh, that advice will you'll see what that advice really means when you do some of this in class. Anyway, one example of current causing magnetic field is the Earth's magnetic field. As the Earth rotates, the molten material on the interior of the Earth rotates too, but it's sloshing around, and it actually rotates at a different speed than the surface of the Earth. The molten material sloshes around. It's not firmly fixed. It's not glued to the Earth's crust, but it circles around at a slower rate. Just as if you try to start spinning a bucket, when you first start spinning, the bucket is spinning really fast, and the water is spinning in the same orientation, but more slowly. That's exactly what's happening if you compare the spin of the Earth's surface to the spin of the molten material in the interior of the Earth. A lot of that molten material is charged, so what you have are charged particles moving in a loop. Specifically, here's the Earth, and there's the Earth's axis tilted at 23.5 degrees relative to the plane of the Earth's orbit around the Sun. So, and the Earth rotates, say, west to east, and so the molten material in the interior of the Earth rotates west to east also, but more slowly. And as a result, if you're sitting here on the surface of the Earth, you're going this way faster. The molten material is going the same way but slower, which means if you pick any point in that molten material, you're getting farther and farther and farther ahead of that point in the molten material as time goes by. In other words, it appears to you as if the molten material is rotating that way, east to west. So, from the perspective of us on the surface, that is the direction of a current loop in the interior of the Earth. And like any other current, it produces magnetic field. The simplest case, a straight current produces field whose field lines are plain old circles. A loop is similar in that the field lines all loop around the current, but the field lines aren't perfectly circular. They're oblong in some sense. So as a result, we get field lines that go around the current. A round trip on the field line encloses the current, but they're not perfect circles. The right-hand rule still applies. Thumb in direction of the current, like this. So deep in the interior of the Earth, closer to the center of the Earth than this flowing current, the field lines are pointing down. But then on the other side, when you're closer to the Earth's surface or at the Earth's surface, farther away from the center than the current represented by my thumb, the field lines are pointing up south to north. So the field lines will look something like this. In other words, here at the tropical and temperate latitudes, the magnetic field lines are just about parallel to the Earth's surface. But up here in the Arctic, down here in the Antarctic, field lines, when you actually get close to one of the Earth's magnetic poles, here or here, the field lines are almost perpendicular to the surface of the Earth. And one thing that that magnetic field does is orient a magnet. One example of a magnet is a compass needle, and so the direction of a magnetic field is always the direction in which the north pole of a magnet, like for example the north pole of a compass needle, points. North pole of a magnet, compass needle, or any other magnet points in the direction of the magnetic field lines. So conveniently, the north pole of the magnet, north pole of the compass needle points toward geographic north. Now let's look at a few examples of a situation where we've got more than one field source, a little bit more complicated. And let's look at it this way. Well, first, let me say one other thing. Here's current coming straight out of the blackboard, and then let's think about the direction of magnetic field right there. Well, that point is on some circle centered on this point is on some magnetic field line, which is a circle centered on the current. So if I draw, say, maybe 1/4 of that circle, it would look like this. And so the direction of the field here would be along the straight line that's tangent to the curve. And as we saw earlier, applying the right-hand rule to the current coming out at you perpendicular to the paper, perpendicular to the blackboard, the field lines flow around counterclockwise. So the field lines are flowing like that. So at this point, the field points that way, along the straight line that's tangent to the field line at that point, and in the correct direction that's consistent with the flow of the field lines. But now notice one thing. This line, of course, is along a line that's tangent to the circle, but think about the line that connects this point to the source, that connects this point to the current. That's a radius of the circular field line on which this point sits. The way geometry works out, radii of a circle are always perpendicular to the tangent lines. So this is a radius, this is a tangent line, and wherever a radius, whatever point on the circle where a radius and tangent line meet, the radius and tangent line are perpendicular to each other, always. Which means we can save ourselves a little bit of work when we're trying to figure out the direction of the field at some point. All we have to do is something like this. So there's the current, and there's the point that we're interested in. Current is coming this way, which means the field lines are flowing counterclockwise again. Just draw a line that connects the source to the point that you're interested in. That, of course, is the radius of the circular field line upon which this point sits. And since the field at this point points along a line that's tangent to the circle, the field here is pointing perpendicular to this line here, because this line is a radius and the tangent lines are always perpendicular to the radii. So the magnetic field must point one way or the other along that line perpendicular to the radius that you just drew. Because we already found that for current flowing this way, the flow of the field lines was counterclockwise. That means in this particular case, the magnetic field has to flow that way, in a direction that's perpendicular to the radius. So, to put it in the form of some 3 steps. First, draw a line from the source to the point that you're interested in. That's a radius of a circular magnetic field line. And point 2, you know that the magnetic field at the point you're interested in is perpendicular to that line you just drew. That means the magnetic field has only 2 possible directions, one way or the other way along that straight tangent line. And which way you figure out by using the right-hand rule. Use the right-hand rule to find the direction. Now let me show you what that looks like in a specific case. So imagine I've got 2 currents in the same vertical plane. Call them B and A. Same vertical plane, and to keep things simple, we'll say that the amount of current in each wire is the same. Now, imagine 2 points that are just symmetric. They're along the plane that bisects the line that connects A and B, and they're, say, way out here and then way out here. We'll call this point 1 and this point 2. What is the net magnetic field? What does the net magnetic field look like at points 1 and 2? The distance between A and one of these points is the same as the distance between B and that point, because these points are both along the plane that bisects the AB line. So we're keeping it simple. This point has an equal distance from A and B, and the current A is equally strong with the current B, which means the magnitude of A's magnetic field here will be the same as the magnitude of B's magnetic field right here, just to keep it simple. And let's do that trick that I just explained to figure out what the direction of the field caused by A is and what the field caused by B is, and then we can figure out what the net field is. Let's do point 1 first. So here's, draw A again, B again, point 1. Start by drawing the line that connects A to the point. We know that the magnetic field will be pointing perpendicular to that line because the field points along a tangent, and tangents are perpendicular to radii, and this is a radius of a circular field line. So the the field from A will be pointing one way or another along that line, and which way you determine by the right-hand rule. This is a current going into the blackboard, so point my thumb into the blackboard. My fingers therefore curl clockwise, which means over here, clockwise movement means here at this point, the field would have to point up and to the left. That's the magnetic field from current A. Now do the same for the magnetic field that comes from current B. There's the line that connects current B and the point we're interested in, and we know that the magnetic field caused by B, the field at this point that's caused by B, has to be perpendicular to that line. So it's along a line like along the line like this. And which way is again determined by the right-hand rule. Current into the blackboard, so thumb into the blackboard. My fingers curl clockwise. So curling clockwise means at this point, curling clockwise around this point means up here, the field must be pointing up and to the right because the field lines are flowing this way. And I try to draw that arrow the same length because the magnitudes of the two fields are the same. So there's B, B. Then the net field is just the sum of those. BA plus BB. Right. The net field points straight up at this point to the left of the AB plane. And notice I'm doing the same old thing. The arrows that represent the things being added are connected tail to tip. And the arrow that represents the sum takes us straight from the beginning of that path to the end of that path. Now, what about the field right here on the other side? So here's A, here's B, here's the plane on which our points sit, and there's our point. So first the field caused by A, draw the line that connects current A to the point that we're interested in. That's a radius of a circular magnetic field line on which this point lies. So the straight line that is tangent to that circle at this point has to be perpendicular to this radius. So it's pointing in this direction or this direction. And again, the specific direction you figure out by the right-hand rule. And by this time, you know that when the current points this way, away from you, perpendicular to the paper, perpendicular to the blackboard, the curl of the field lines is counterclockwise. So up here, counterclockwise means down, down and to the left. So the field lines are flowing this way. And for BB, do the same. Here's the line that connects B and our point. The field caused by B is perpendicular to that line, so it's along some line like that. And which way does the magnetic field point along this line, this way or this way. Remember, the field lines are flowing counterclockwise. So for the circle centered on B, the circular field line centered on B and flowing counterclockwise, up here at X, it's flowing this way, which is down and to the right. So that's the direction of B, and then when you add those two to get the net force, you've got BA, and add to it BB, and then the net force of the net field is straight down, just as the field on the other side was straight up. Okay, so the most of what we need here is qualitative and pictorial rather than quantitative. The only equation that matters at all is the equation that tells us the magnitude of the magnetic field caused by a long straight wire when you're a distance d meters away from the wire. And the magnitude of that field is this constant lowercase Greek letter mu with a subscript 0. That's a number that that's a famous number in electrodynamics. It's a number you can look up if you ever have to do a calculation, times the current divided by 2 pi and the distance away from the current. So in other words, if you stay at the same point, in other words, make d a constant, magnetic field strength is directly proportional to the current. Right? The strength of the field is directly proportional to the size of the source. That's just the same kind of thing we had when dealing with electric fields caused by one lump of charge. And if you keep the same current but move around to different points, in other words, D can now change, then the magnitude of the magnetic field is inversely proportional to the distance, which is similar but not the same as what we saw in electric fields. The magnitude of the electric field was inversely proportional to distance squared. Here, the magnitude of magnetic field is inversely proportional to just distance to the first power. But in both cases, the field gets weaker as you go farther away, because there's some kind of inverse proportionality between field and distance. Okay, those are all the basic ideas. Just about everything else we do is an application of those ideas. We'll try some of this in class. This was just our introduction to magnetic field. The last video that you'll see will be an introduction to magnetic force, which turns out to be, again, more complicated than electric force.